is your Bluetooth chip leaking secrets via RF signals? And Elena is going to give the talk.
Thank you for the introduction. It's a joint work with my two PhD students, Yaning Zhi and Reisa Wang. The motivation behind this work was to find out whether millions of Bluetooth devices which contain cryptographic accelerators leak secret. And our contribution was that we demonstrate the first attack which extracts secret key from a crypto accelerator. It's advanced encryption standard with 128-bit key for a side channel, which you may not be aware, it's RF signal. So it's actually carrier RF, which we capture using software-defined radio, and we extract side channel from it. I would like to give you some previous work on previous attacks. It's not a popular side channel, but there were some attacks presented. The first one was in CCS 2018, so some years ago. They extracted secret key from a software implementation of advanced encryption standard, which was programmed in Cortex-M4. This is a processor which is contained within that chip. It's the same target chip as the one we're using in this attack. And it was a tiny IF implementation, meaning it processes things byte by byte. It's actually easiest to attack. So you can see from this table that they use a template attack as a method. And first attack was on a 10-meter distance in a lab. And then you need to repeat the same encryption 500 times to reduce the noise, increase signal-to-noise ratio. And they needed 1,400 something traces to break it. Then they also did an attack on a closer distance in an office environment, which is clearly more noisy. And then they needed same number of repetitions, about 52K traces. So it's quite massive attack. And then 2 years ago, after that, the same team of people presented a paper in Chess where they repeated template attack on a 15 meters distance in an office environment, much longer, which 1,000 repetitions, you see it's double because the noise is much higher. It's a longer distance. And they needed some enumeration to power 23 and 5K traces for the attack. Same year, we presented an attack which used neural networks to model leakage. And you can see it was in an office environment. What we wanted to achieve is using single repetition of the same encryption, not multiple. And we succeeded to do it with some effort. So we need 341 trace on average to recover the key from a single repetition with no enumeration. But I would like to stress this is a software implementation of advanced encryption standard, tiny IAS, which is very easy to break. It's unprotected. So what the question we had ever since, myself personally at least, can we break an IIS hardware crypto accelerator which is available on the same chip? Because why would you program something in Cortex if you have a hardware accelerator on this chip, crypto accelerator, sorry. But apparently it's very difficult, and the author of the CCS paper, the first time it was published, they say we cannot break it, it doesn't leak, apparently. And we were trying to do it for quite some years. One thing which complicates the attack, previous attacks were in electronic codebook mode, where you have complete control of plain text and ciphertext. And this hardware, this crypto accelerator, which is on this chip, it implements advanced encryption standard in CCS mode of encryption. So you use counters to produce key streams. That's I will have a diagram in a slide or so. And then also the clock which is used for this crypto accelerator is different from the clock which is used for Cortex. Cortex runs at 64 megahertz. This advanced encryption standard runs at 16 megahertz. So it wasn't very clear whether we get any leakage from this ASIC implementation of advanced encryption standard. So our questions which we wanted to answer is, can we extract encryption key from RF carrier signal on a distance? And one thing which I would like to stress, why it differs from power or EM analysis. Power, you would need to soldier in an element, so it leaves tamper evidence. EM, you need to be on a millimeter distance from your target device. Here, we're talking about meters from the target device with no tamper evidence left because you don't modify device in any way. This is the way I will try to first explain you, because I assume most of you are not engineers, but cryptographers. let's discuss why mixed signal circuit may leak secret. What's so special about having a mixed signal circuit? Like think about two glasses on the same surface on a table. We knock with some stick on one of them, there will be circles on the surface. And we may get circles also on the surface of a second glass because they share the common surface. They stay in the common surface. And also think the closer they are, probably the more disturbances we will get. The more isolated they are, the less disturbances we will get. And it's similar in mixed signal circuits because we have a digital part where we have this crypto accelerator. We also have Cortex there. And there are a bunch of other elements, and then we have an analog part with some elements. So what happens is that digital noise produced during the computation, key-dependent computation of advanced encryption standard, it propagates to the analog parts. It leaks there through a number of physical phenomena. One of them is substrate coupling. So we get some noise propagating, affecting elements in the analog part. And one element I would like to particularly pay attention, so this is what I said about the substrate coupling, is this VCO, voltage control oscillator, which is actually a block which generates your carrier signal based on the input voltage. So if that digital noise affects that input voltage and the block, that carrier signal may get slightly modulated and then transmitted. So what will happen, that side channels are getting entangled into that transmitted signal. It modulates it by the amplitude. At least we are exploiting the amplitude in our attack. And this is why we can get it on a distance from device by demodulating these RF signals. So here is our attack setup. Our target is Nordic semiconductor chip, NRF 52832 system on a chip. Our measurement setup is we basically have it in an office. You see this large antenna with a target device on 1 meter distance. We could make it larger. In the previous attack, we made it on a 15 meters, but this previous attack was done during COVID time, so nobody was in the office. Now, unfortunately, we cannot afford it. We don't have COVID, so we hijacked one office of a person who is away somewhere for a year, because you will see this attack took us quite some days to do. So we basically put a label, don't go in the office, for anybody not to disturb our measurements. And that's why it's just 1 meter. It could be longer. It actually doesn't matter because it's a well-formed signal we are capturing already. So we're using that white box, which you see, it's a software-defined radio. It's actually cost $10,000 US. It's quite expensive equipment. We tried first with the cheaper one, it wasn't working. With this one, we can sample at the frequency of 50 megahertz. So it's roughly 3.1 something points per clock cycle we get, because obviously the more you get, the better. And important question is at which center receiving frequency we are demodulating. So it is the Bluetooth band frequency 2.4 gigahertz plus a multiple of the clock frequency. And well, you can see details, so we can discuss it offline, why and what, but that's basically the center receiving frequency at which we are receiving, demodulating, and we are getting these side channels, which look like normal power or EM near field trace, more or less. It actually looks like a power trace. Key recovery methods are standard, more or less. We try both profiled and not profile attack settings. Profiled is good old correlation analysis. That was the first attack we succeeded. And then we also tried deep learning-based analysis. The reason we tried it later is that you need a lot of time to capture the training set. Months, we're talking about months. So this is a diagram of advanced encryption standard, 10 rounds, 128-bit key. As an attack point, we use SBox input in the last round. And the reason for this, why not in the first, probably you have an idea, it's because it's a counter encryption. So in the counter encryption, we can only control the nonce, which is 8-byte. So even if we recover everything, it would be just 8-byte of a key. There are techniques actually to propagate it, but we noticed that the leakage is not that strong. So the SBox input in the last round was leaking strongest. It was leaking stronger than more traditional leakage model for hardware implementation, which is typically a distance, Hamming distance between ciphertext and SBox input. It also leaks, but it leaks less. This one was leaking stronger. So we had a nice talk yesterday about authenticated encryption. I just included this one slide to remind you. So counter mode, 0 block is used for producing keystream S0, which is used to encrypt the MAC. MAC is produced in the cipherbot blockchaining mode. 32-bit MAC is used. And first block and all others, if you have longer messages, are used for producing key streams, which you XOR with the key. So this is why I'm saying that the first round attack is not that easy, because the nonce, which counter block 1 contains, is 8 bytes only. That's what you can control. So we are attacking, as I said, ciphertext block 1, the output. So sorry, that was too quick. So this was our first successful attacks. We're using 180,000 traces. Each of them is computed as an average of 10,000 repeated encryptions. So in total, it is 1.8 billion single traces. It's a very massive attack. And you see the number of days we need to capture this set. It's a lot. And you can see that we're heroes because we actually try 2 different keys just to make sure that it's a consistent result. We also tried in 2 different settings. So multiply 18.9 by 4 to get the total number of days we were capturing for this table. So with cable means coaxial cable. We connected through coaxial table to device under attack, because coaxial table gives you more or less noise-free environment, more or less free from environmental noise. So if you would clean environmental noise, this is roughly what you would get. So in that column where you see 2, 2, 3, 4, it's the number of key bytes which we are not recovering correctly. And then one can enumerate, because you can get some statistic of how many number of bytes you expect not to be able to enumerate. Then you can take all possible choices, 16 choice K, where K is the number of bytes you expect to fail. And also we noticed that it is a better strategy to not to try to get all the bytes, because there are some tough ones. It's quite different, the difficulty of recovering each byte, completely non-uniform. So there are some tough ones which just we would need to double. And even then we don't recover, in fact. Even if we double, we try doubling. So this was our first successful result. Then we tried deep learning. So we spent months on capturing this training set from 4 different devices, which are certainly different from the ones we used for the attack. And because you want to use different devices for profiling attack, because then you kind of cancel out the effect of manufacturing process variation, which is quite important effect. It's very different what you get. So you see, we actually recover all the bytes for the cable capture traces, and we don't recover 1 in both cases for the antenna capture traces. So then we reduced, we half, we just went by binary search. We half the number of traces. And then here are the results for correlation analysis. We're still fine for cable. We are not fine for antenna because it's too long. You cannot enumerate this. And then with deep learning based analysis, it was still quite good, so that we further halved. This is already like 5 days of capture, getting there maybe another few times to half, and we have a nice working practical attack. So this is the correlation. You see, for 1 key, we can still do it by correlation, but for another one, it's kind of getting a year and a half, a bit too long. Then we cannot get it by antenna. In deep learning, it's still working. And what I didn't say about deep learning, but I'm running out of time, we're using ensemble of 3 models constructed in a different way. We give all the data available so you can see our structures and stuff. And that's why we know which bytes are wrong, in fact. For correlation analysis, we don't. And now mitigation strategies. What do we need with these glasses? Isolate them, put them further apart from each other, maybe change the substrate. And these are the actual mitigation strategy. At the circuit level, engineers are fighting to stop this noise from propagating, yet purely for functional reasons, because functionality wouldn't work, but they are not taking security as a design objective. So that's why it's nice to be aware of this type of attacks. Maybe they will try a bit harder to isolate, and there are known techniques in VLSI for this. Algorithm level, we can apply masking, shuffling. There are some other countermeasures like local randomization of duplication. We have a paper on this. It's quite nice. On protocol level, update the key frequently and force fresh nonce. What I mean by force is actually generating a nonce on device. For example, the way we do it in Kyber, encapsulation, 256-bit message is generated at random on device, not left to the user to decide. If we would do it here, this attack would not be possible because we wouldn't be able to average. It would always be a fresh nonce for each encryption. We notified Nordic Semiconductor, gave them all our scripts and data for independent evaluation. And to conclude, it's the first successful attacks. We need to be aware of this RF side channel. Security implication, you see it's a challenging attack, but we keep improving this. This weekend, we already have a slightly better results. I think we can do it like with 30K traces now, and probably it will keep getting down. It's not limited to Bluetooth, nothing special about that chip. Be aware when you integrate antenna or anything from radio transmission chain in your chip, you may be opening some new ways, new attack vectors. And key takeaway, we need proactive defenses against this type of RF-based attacks before they scale. Thank you for your attention.